Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1958, Thomas Kuhn, a physicist turned historian and philosopher of science, began drafting a manuscript that would shake the very foundations of how we understand scientific progress. This work, eventually published in 1962 as The Structure of Scientific Revolutions, did something unprecedented. It challenged the long-held, comfortable positivist view of science as a steady, linear march toward truth, achieved through the accumulation of empirical evidence. Kuhn instead proposed a model of scientific advancement, punctuated by radical upheavals, or revolutions, that dramatically altered the course of scientific inquiry. At the heart of Kuhn's thesis lies the concept of a paradigm. A paradigm, in a Kuhnian sense, transcends a mere theory or model. It encompasses the entire constellation of beliefs, values, techniques, and shared exemplars that define a scientific community's view of the world and its proper domain of inquiry. The paradigm dictates which questions are deemed worth pursuing within a given field, what methods are considered legitimate for seeking answers, and what standards are used to evaluate the results. It provides a framework through which scientists perceive and interpret data. Prior to Kuhn, the prevailing view, heavily influenced by logical positivism, posited that science progresses through the gradual accumulation of objective facts, rigorously tested and verified through observation and experiment. Any new theory had to either be consistent with prior theories or be the generalization of them. Kuhn argued that this picture was inadequate, that it failed to account for the profound and often discontinuous shifts in scientific thought that history reveals. He looked at the historical record and saw something very different: periods of relative stability, normal science, which are occasionally interrupted by periods of revolutionary change. Kuhn described normal science as the day-to-day work of scientists operating within a dominant paradigm. It is primarily a puzzle-solving activity, focused on refining, extending, and articulating the existing paradigm. During normal science, scientists do not typically question the fundamental assumptions of their field. Instead, they accept the paradigm as a given and work to resolve the puzzles that arise within it. This puzzle-solving strengthens the paradigm's grip and expands its domain. To illustrate this point, Kuhn frequently employed the historical example of the shift from Ptolemaic to Copernican astronomy. The Ptolemaic system, with its geocentric model of the universe, had served as the dominant paradigm for centuries. However, it became increasingly burdened by ad hoc modifications, epicycles upon epicycles, designed to reconcile its predictions with observed planetary motions. The Copernican revolution, with its heliocentric model, offered a radically different perspective. This shift involved more than simply rearranging the positions of the Earth and the Sun. It required a wholesale change in the accepted framework for understanding the cosmos, including new assumptions about motion, gravity, and the nature of observation. The Ptolemaic and Copernican systems were, Kuhn argued, incommensurable. They operated on different assumptions, employed different concepts, and addressed different problems, making any direct comparison or rational choice exceedingly difficult. Even the data were theory-laden. Ptolemaic astronomers saw one thing while Copernican astronomers saw another. Kuhn's work posed a direct challenge to the philosopher Karl Popper's falsificationism, which held that science progresses by formulating bold conjectures and then attempting to falsify them through rigorous testing. For Popper, the hallmark of a scientific theory was its falsifiability. Kuhn, however, argued that scientists rarely, if ever, abandon a theory simply because it is confronted with contradictory evidence. During normal science, anomalies, instances where experimental results deviate from theoretical predictions, are often set aside, explained away, or attributed to experimental error. Only when anomalies become persistent, pervasive, undermine the core tenets of the paradigm does a crisis ensue, potentially leading to a scientific Kuhn's background as a physicist profoundly shaped his conception of scientific change. He had first-hand experience with the way scientific communities operate, the kinds of problems they address, and the criteria they use to evaluate success. Moreover, his experience with the transition from classical to quantum mechanics impressed upon him the fact that scientific change could be revolutionary, involving a complete break with the. Beyond his scientific background, Kuhn's intellectual development was also significantly influenced by Gestalt psychology and the historical approach to science pioneered by Alexandre Koyré. His exploration of Gestalt psychology during his transition into history and philosophy of science contributed to his emphasis on the role of perception and interpretation in shaping scientific knowledge. Gestalt psychology stresses the role of the mind in organizing sensory information into coherent wholes, suggesting that our perception of the world actively constructs and interprets rather than passively receiving stimuli. He drew a parallel between the way individuals experience a Gestalt switch, where a visual pattern suddenly reconfigures itself, the way scientists experience a paradigm shift, where their entire worldview is transformed. The impact of Alexandre Koyré, who emphasized the significance of metaphysical commitments in scientific thought, was also profound. Koyré argued that scientific revolutions are not simply driven by empirical discoveries, but also by changes in the underlying philosophical assumptions that guide scientific inquiry. Kuhn took up this theme, arguing that paradigms are not mere sets of empirical generalizations, but also embody metaphysical commitments about the nature of reality. Koyré's historical research demonstrated the importance of understanding the historical context in which scientific ideas developed, a context shaped by philosophical, religious, and social factors. Kuhn followed Koyré's lead, stressing that to truly understand scientific change, one must delve into the complex interplay of intellectual, social, and cultural forces that shape scientific communities. The structure of scientific revolutions, as articulated by Thomas Kuhn, represents a cyclical process characterized by distinct stages: normal science, anomalies, crisis, revolution, and a return to new normal science. This framework fundamentally challenges the traditional, linear view of scientific progress as a steady accumulation of knowledge. Instead, Kuhn posits that science advances through paradigm shifts, periods of radical conceptual change that alter the very foundations of scientific inquiry. Normal science, the initial stage, describes the routine work of scientists operating within an established paradigm. A paradigm, for Kuhn, stands a shared set of beliefs, values, techniques, and assumptions that define a scientific discipline and guide its research. During normal science, scientists engage in puzzle solving, attempting to refine and extend the existing paradigm to account for new observations and phenomena. This involves testing the paradigm's predictions, developing new instruments, and applying the paradigm to novel domains. A fundamental characteristic of normal science involves adherence to the prevailing paradigm, with scientists typically working to confirm and strengthen its foundations, not to challenge them. Anomalies play a crucial role in undermining the existing paradigm. Anomalies represent persistent observations or experimental results that cannot be adequately explained within the framework of the current paradigm. Initially, anomalies generate dismissed as measurement errors or experimental artifacts. Scientists often attempt to assimilate them into the existing paradigm through ad hoc modifications or reinterpretations. However, the accumulation of significant and persistent anomalies can lead to a growing sense of unease and dissatisfaction within the scientific community. The emergence of a crisis marks a turning point in the scientific process. A crisis arises when anomalies become so numerous and profound that they undermine confidence in the existing paradigm. Scientists begin to question the fundamental assumptions and principles of the paradigm, and alternative theories and explanations emerge. During a crisis, the rules of normal science begin to break down, and scientists engage in more speculative and radical thinking. The field enters a state of intellectual ferment, characterized by intense debate and competition among rival viewpoints. A scientific revolution occurs when a new paradigm emerges that successfully resolves the crisis and replaces the old paradigm. Paradigm shifts involve a fundamental change in the way scientists perceive and interact with the world. The new paradigm offers a new set of concepts, theories, and methods for understanding nature. It provides scientists with a new framework for interpreting data, designing experiments, and solving problems. Kuhn emphasizes the incommensurability of competing paradigms. Incommensurability means that the concepts, methods, and standards of evaluation differ so radically across paradigms that it becomes impossible to directly compare them or rationally choose between them. Scientists operating within different paradigms effectively live in different worlds, observing different things and interpreting them in fundamentally different. The chemical revolution, in which Antoine Lavoisier's oxygen theory replaced phlogiston theory, serves as a prominent example of a paradigm shift. The phlogiston theory, prevalent in the 18th century, proposed that combustible substances contained a violet element called phlogiston, which released during burning. Lavoisier's experiments demonstrated that combustion involves the combination of substances with oxygen, rather than the release of phlogiston. This new theory revolutionized chemistry, leading to a accurate understanding of chemical reactions and their composition. The Newtonian revolution in physics exemplifies another paradigm shift. Newtonian mechanics replaced Aristotelian physics, offering a new set of concepts, laws, and methods for understanding motion, gravity, and the structure of the universe. Newtonian physics emphasized the importance of mathematical laws and quantitative measurements, leading to a more precise and predictive science. Kuhn contends that scientific revolutions are not merely about accumulating more knowledge, but about fundamental changes in the ways scientists perceive and interact with. Paradigm shifts involve a transformation of the scientific worldview, affecting the kinds of questions scientists ask, the methods they employ, or the standards they use to evaluate evidence. Kuhn's analysis challenges logical positivism, which emphasized observation and verification as the primary means of acquiring scientific knowledge. Logical positivists believed that scientific theories could be reduced to observational statements and that scientific progress involved the gradual accumulation of verified knowledge. Kuhn argued that observation is always theory-laden and that scientific knowledge is shaped by the prevailing paradigm. He rejected the notion of a neutral, objective observation, emphasizing that scientists interpret data through the lens of their theoretical commitments. Kuhn's view of progress departs from the logical positivist view. Logical positivists viewed scientific progress as a linear and cumulative process, with each new theory building upon and extending previous theories. Kuhn argued that scientific progress is cyclical and discontinuous, involving periods of normal science punctuated by revolutionary paradigm shifts. He suggested that new paradigms supersede old paradigms, rather than building upon them. The transition from one paradigm to another involves a radical break with the. Kuhn's ideas draw upon the early work of Jean Piaget on the development of children's cognitive schemas. Piaget proposed that children developmental frameworks, or schemas, for organizing and interpreting their experiences. As children encounter new information, they assimilate it into their existing schemas or accommodate their schemas to account for the new information. Kuhn saw parallels between this process and the way scientists develop and change their paradigms. He argued that scientists, like children, assimilate new information into their existing paradigms until anomalies force them to accommodate their paradigms or adopt new ones. The echoes of Thomas Kuhn's The Structure of Scientific Revolutions continue to reverberate through the halls of academia, reshaping our understanding of scientific progress and knowledge creation. The book's long-term impact on the philosophy of science is undeniable. It prompted a shift away from purely logical analyses of scientific theories toward a more historically and sociologically informed perspective. Its conceptual framework provided a new lens through which to examine scientific revolutions, questioning traditional notions of linear, cumulative progress. One of the most significant contributions of The Structure of Scientific Revolutions lies in its introduction of the concept of a paradigm. Kuhn defined a paradigm as a set of shared beliefs, values, techniques and assumptions that guide scientific research within a particular discipline. During periods of normal science, scientists work within the confines of a dominant paradigm, solving puzzles and refining existing theories. However, as anomalies accumulate and the paradigm's ability to explain new phenomena diminishes, a crisis emerges, potentially leading to a scientific revolution. This revolution involves the overthrow of the old paradigm and the adoption of a new one, which offers a more comprehensive and coherent framework for understanding the natural world. Central to Kuhn's thesis is the idea of incommensurability. Incommensurability asserts that different paradigms are so fundamentally different that they cannot be directly compared or evaluated using a common set of standards. This challenges the notion of objective progress in science, as the adoption of a new paradigm involves a shift in perspective and values, rather than a purely rational choice based on empirical evidence. The specific claim of incommensurable observation languages gained particular attention. Kuhn argued that scientists operating under different paradigms literally see different things when observing the same phenomena. Because their observations are theory-laden and shaped by their background assumptions, Kuhn's work faced criticism, particularly concerning his alleged relativism. Critics argued that incommensurability implies that there are no objective standards for evaluating scientific theories, and that the choice between paradigms is ultimately a matter of faith or social consensus. Kuhn responded to these criticisms by clarifying that he did not reject the possibility of rational debate or empirical evidence in science. Instead, he argued that the criteria for evaluating scientific theories are themselves paradigm-dependent, and that the transition from one paradigm to another involves a complex process of negotiation and persuasion within the scientific community. Despite the controversies, Kuhn's ideas profoundly influenced the philosophy of science, prompting a reassessment of traditional views of scientific objectivity and rationality. His focus on the social and historical context of scientific knowledge paved the way for the development of science and technology studies, which examines the social, political, and cultural factors that shape scientific research and technological innovation. Influential sociologists of scientific knowledge, such as David Bloor and Barry Barnes, directly built upon Kuhn's work. arguing that scientific knowledge is socially constructed and influenced by the interests and values of the scientific community. This perspective, known as the strong program in the sociology of scientific knowledge, views science as a social activity, subject to the same influences as other human endeavors. Beyond the philosophy of science, Kuhn's ideas have found application in other disciplines, including the social sciences and humanities. The concept of paradigm shifts has been used to analyze changes in political ideologies, artistic movements, and cultural norms. For example, historians have drawn parallels between scientific revolutions and periods of social and political upheaval, arguing that these transitions involve a similar process of paradigm change and the redefinition of fundamental values. Similarly, literary scholars have used Kuhn's framework to analyze shifts in literary styles and genres, arguing that these changes reflect underlying shifts in cultural assumptions and beliefs. Kuhn's work also influenced later philosophers of science, such as Paul Feyerabend and Irela Cartos. Feyerabend, known for his advocacy of epistemological anarchism, embraced Kuhn's critique of scientific method, arguing that there are no fixed rules or procedures that guarantee scientific progress. Cartos, on the other hand, sought to reconcile Kuhn's historical perspective with a more rationalist view of science, proposing the concept of research programs as a way to account for the continuity and progress of scientific knowledge. Even today, Kuhn's concepts of paradigm, normal science, and incommensurability remain relevant for understanding scientific progress and the dynamics of scientific communities. In an era of rapid scientific and technological development, Kuhn's emphasis on the social and historical context of scientific knowledge has become increasingly important. As scientific research becomes more interdisciplinary and collaborative, Kuhn's insights into the dynamics of scientific communities and the role of shared beliefs and values offer valuable tools for navigating the complexities of modern science. The enduring power of the structure of scientific revolutions lies in its ability to challenge traditional assumptions about the nature of scientific knowledge and to offer a fresh perspective on the complex and often non-linear nature of scientific change. By shifting the focus of philosophy of science from logical analysis to historical and sociological understanding, Kuhn opened up new avenues for exploring the intricacies of scientific practice and the social construction of knowledge. His work continues to shape debates about scientific objectivity and the nature of scientific progress, solidifying his place as one of the most influential thinkers of the 20th century, a legacy secured by challenging assumptions and forever altering the course of intellectual discourse.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.